So today's topic is going to focus a lot on some equations and math that is used to calculate populations, birth rates, growth rates of populations, that sort of thing. Okay, so just a quick reminder of what a population is, right? Population is our individual organisms that interact with one another and the environment. Okay, and so we're going to be looking at adaptations. So many adaptations in these organisms are going to be related to their ability to obtain and to use energy and or matter in a particular environment. Remember, these adaptations are going to be, they stick around if they're beneficial to that particular environment. And most of them are going to be related to, again, their ability to either obtain, to either get, or to use energy and matter. So population growth dynamics is going to depend on a couple of factors, and we're going to use this equation to talk about it. So the first part of this is going to be the dn. So the d, the lowercase d there, is actually for delta, which is represented as a triangle, which is change. But unfortunately, the triangle doesn't print on everything. So a lot of times you'll see lowercase d. And so the lowercase d is for delta, which again is represented as the triangle, which means change. So this really ends up looking like this. So now I have my delta n, right? N is my population size. So capital N is population size. The capital B there is the birth rate. So birth rate. So the capital D is going to be the death rate. And the lowercase there is going to be time. So what this equation boils down to is that our change in our population size over time is equal to the birth rate minus the death rate. You will also talk about what's called our per capita, we're going to do examples with these. Our per capita birth rate or death rate, you can do it either way. Okay, the basics of what it means is the same when we talk about per capita. So our per capita birth rate or death rate is going to be your numbers of births or deaths per unit of time by an average member of the population. Okay, think of it as almost like a percent change when you factor in the entire population. Okay, but that's basically how you'll calculate it. You'll calculate it very similar to how you would calculate a percent. Right? You take your birth rate or death rate over the entire population. Like I said, let's look at some examples of these. Okay, so let's look at some examples of this. So in this particular scenario here, I've got a population of 3,000 June beetles, and over the course of 1 month, I note 400 births and 150 deaths. So what is the change in population of the beetles? So that's going to be our first equation, right? Our change in population over our change in time is birth rate minus death rate. So my change in beetle size, my change in time was 1 month. My birth rate was 400, my death rate was 150. So meaning then that my change in the population of beetles, is going to be 250 beetles per month. And because this is a positive 250 beetles, that tells me my population is increasing. Had it been a negative, had it been 400 deaths and 150 births, then my population would be decreasing. So our follow-up question here then now is, what is our per capita rate of growth? So to know per capita rate of growth, I do need to know the rate of growth, which we calculated the time before, right? So my rate of growth is 250. So my per capita rate of growth, remember I told you to calculate it like a percent, is 250 beetles per month per individual, right? So I need to put it over the entire population, which gives me 0.0833 individual per month per capita, So what does this mean? Well, what this means is that if we think back to the previous slide where we said that per capita birth rate or death rate is my number of births or deaths per unit of time by an average member of the population. So what this means is that an average beetle in this population of 3,000 beetles is having 0.0833 births each month. Yes, I know a beetle can't give birth to like part of a beetle. Okay? Again, this is an average because I've got deaths that are happening, I've got births that are happening. So an average beetle has a 0.0833 births per month. Basically meaning that there's an 8.3% increase in the beetle population as a whole each month. So I can use this number to help predict future beetle populations. So for example, let's say I asked how many beetles would you expect after 2 months? Okay, how many beetles would I expect after 2 months? So my first month, if I have this per capita growth rate, I have 3,000 beetles times 0.0833, meaning I'm going to add 250 beetles to my population. So after month 1, and this is important that we go month by month. After month 1, I have 3,250 beetles in my population. But remember, per capita is relative. So if my per capita growth rate is still 0.0833, well, now I'm applying that to a bigger population. If my average beetle in my population is having 0.0833 births, and I have more than 3,000 beetles, then I'm going to have more than a growth of 250. So my second month, okay, if you make sure you have this down because I'm going to erase some stuff so I can get some more space. So my second month now, I have 3,250 beetles times that average growth rate of 0.0833 per beetle, which this time now gives me a growth this month of 270.83225 beetles. So now when I add that number to 3,250, now after the second month, I have 3,520.83225 beetles. Again, remember it's an average, so I can have a part of a beetle. Okay, this is a different answer than if I had just added 250 both times. Okay, so you need to make sure you realize that as the population grows, because per capita is relative to the population, like a percent, it is going to change with the population. And so you can't just blanket say, oh, it's going to add 250 beetles every single time. Okay, again, we'll do practice you'll do practice problems with this, okay, so that you can get a little bit more used to this. So what if we're talking about exponential growth? So where basically reproduction is happening without any kind of constraints. Okay? So there's no issues with reproduction. There's no food problems. There's no space problems. There's no water problems. No competition. Okay? I get this J shape on the graph like I see down here because I get this very, very rapid increase. As a general rule, things are doubling. Okay? And this is unsustainable. This cannot last forever. However, if a population is in exponential growth, then this is the equation we can use to calculate things, where R max is that per capita growth rate of the population. This is what we just did in the June beetle problem, right? We asked what it would be after 2 months, right? So our change in time down here was 2 months. We wanted to know what our change in our population would be. Our max for that population was 0.833. So we had to keep multiplying it, right? We did 0.833 times 3,000 and then 0.833 times 3,250. This is usually helpful to develop a table for this to see this growth happening. But this is exactly what we just did on the June beetle problem. The equation looks a little bit different, but the Rmax came from the birth rate and the death rate. And you're going to do this again for each, if I wanted over years, like maybe over 10 years, then I would do it for each year, right? I'd calculate the new population, multiply it by the per capita growth rate, and keep going from there. Eventually, this will stop, again, because you'll have those reproductive constraints. So when those constraints kick in, we start to see this logistical growth. So the limits of our population growth could be due to a number of things. Okay? They could be due to density-dependent factors, which are dependent upon literally the density of the organisms, meaning how many organisms are in that particular area. And as we increase the density of the organisms in that particular area, they start to compete, right? They compete for water, they compete for food, shelter, mate. Disease is spread faster in areas that are more dense. Predation is easier for organisms in areas that are more dense. Density independent factors, they're going to occur regardless of the density of the organisms. Our most common examples of these are things like natural disasters. A forest fire, lightning strikes and starts a forest fire. The lightning didn't care. It's not more likely to start a forest fire in an area where there's more deer versus versus few deer. It doesn't matter about the density of the organisms. A tornado coming through. Again, the tornado isn't choosy about whether it's a densely populated city or a rural field. Okay, so our equation for this is going to change a little bit when we start to bring in this carrying capacity. Remember carrying capacity from your freshman year, right? The amount of individuals that the available resources can support. Again, remember your carrying capacity is the amount of individuals that the resources can support. So in this particular graph, our carrying capacity stays the same. You'll notice it's a horizontal line and it stays the same. And so when the organism number is very small, we can have that J-shaped exponential growth because there's no constraints. I've got plenty of resources available. However, as we approach the maximum that they can support, that the resources can support, our growth rate slows down, okay? Because once we go up and over that carrying capacity, organisms are going to start to die off because there's not enough resources to support them. Carrying capacity is represented by a capital K, okay? And we get this sigmoid or S-shaped curve. Instead of a J shape, we see the S shape when we are talking about carrying capacity problems or logistic growth. Before it was exponential growth, when it was out of, growing without constraint. Logistic growth is when we start to bring those constraints in. And so this time, our equation, you'll notice the first part is very similar, but then it brings in the carrying capacity, and we'll look at an example of that. So let's look at butterflies first. So I have a population of 300 butterflies, and it's telling me it exhibits logistic growth. If the carrying capacity, so I'm going to have that S-shaped curve there. If the carrying capacity is 500 butterflies and R is 0.1, so we know our Rmax now, what is the population growth rate? In other words, how many individuals are added to the population in one generation? So my population growth rate is asking me how many individuals am I going to add in here. Okay, well, my change in population is going to be my Rmax. And remember, you have a formula chart, right? Use it so you can get used to that, right? Rmax times N, right, over K. Whoops. I did it backwards. Yeah, no, I didn't. K minus N divided by K. Right? So I've got 0.1 is my R. My population is at 300. My carrying capacity is 500 minus my population. Basically, how much room do I have to grow divided by my carrying capacity. You'll notice I didn't take into account my change in time because my change in time is 1. It said 1 generation. If it said 1 month or 1 year, I don't have to worry about it because I'm dividing by 1. If it's different than that, then that will be an issue. So when I plug this into my calculator and I solve, it becomes 12 butterflies. Okay, so my population growth rate in one generation is that this population of butterflies will add 12 butterflies to it. So it is a growing population. Let's look at the one with the crows below it. So a population of 250 crows increases by 21 individuals and has a carrying capacity of 400. What is the growth rate for the crows? So I want the growth rate here. So this time I know that my change in population is 21. What I don't know is my R max. Okay, I know my population size, which is 250. Okay, I know my carrying capacity, which is 400. Again, I know my population size. I know my carrying capacity. Okay, and now I just solve. And when I solve for this, I get 0.224 as my population growth rate. So this population of crows is increasing pretty quickly right now at a faster rate than the population of butterflies that was only increasing at a rate of 0.1. Okay, so we'll do a lot of practice problems with these so that you can become a little bit more comfortable with these particular equations. Again, they are also on your formula chart.